Justin Miller, Extra Call Physics here, and we want to continue onward looking at some capacitors, and hey, let's just go with that. So now we want to start discussing different ways of connecting multiple capacitors in a network, ultimately, and to see how they behave, and how we can represent those capacitors and the overall capacitance of the system. So we're going to look at capacitors in series and parallel configurations. So first off, we got to know some things about how we are going to draw out capacitors in systems and kind of go from there. So symbolically, capacitor shown as this. Say that it has some capacitance C. It looks like two parallel plates. This is generally how you'll see a capacitor in a circuit diagram, or you may see it like this as well. We're going to stick with this notation. This has the one-way aspect of a capacitor. Some capacitors you can only hook up one way, where the negative terminal has to trace back to the negative terminal of the battery, positive terminal of the capacitor traces back to the positive terminal of the battery. Not all capacitors are like that, but some are one way, or you can only have them in the circuit one way to work properly. We're just going to use this one though. And then we've also got a source potential. Shown as we got a big bar, little bar, and for source potentials we'll use that script E to show its voltage, and the big bar here is the positive terminal, the little bar is the negative terminal of the battery or the power supply. The positive terminal is long, negative terminal is small, and then we know which way it's kind of connected with things. So a singular capacitor in a circuit diagram is connected to a source potential circuit diagram. A single capacitor is connected to a source potential like so. What do we have? Well, we just got ourselves some source potential. Like this. We've got, there's our source, there's our capacitor, and all this stuff, any just pathway you have that's just a solid line, is just some conductive pathway. Generally, you think of it as some wire, that's fine. Conductive pathway wire connections. That's it. We've got a single capacitor, the source potential, and what do we have? Well, again, don't have to always draw this in, but the source potential has the positive terminal and the negative terminal, and that directly associates with what the positive side and the negative side of the capacitor will be when it's fully charged. So for now, we're going to assume that capacitors are fully charged in the systems. Enough time's gone by for that to happen, and this would be the plus side, this would be the minus side of the capacitor itself. The capacitor has some potential difference across its plates, It stores some total charge separation such that C is defined as Q divided by delta V, where delta V where delta V is equal to the source potential when C is fully charged. Let's say when the capacitor. So that is to say that C is going to be Q total divided by E when fully charged. All right. So that's what we've got going on with the singular capacitor. Again, if we know the source potential, we know the capacitance of the capacitor that we're utilizing, we can go ahead and figure out what is the total charge that has separated, or total charge stored, we often say. But what we want to do is not just look at a single capacitor, because that's kind of boring. Like, oh, one capacitor. Let's look at multiple capacitors connected. So, series. Configuration. Series just means they're consecutively linked together. So if we have, say, 2 or 3 or n capacitors in series, what does it look like? Well, we have one capacitor connected to another capacitor, connected to another capacitor, and they just keep on going. We could say that this is a capacitor C1, a C2, C3, and if we wanted to, we could connect this to some source potential, boom, and have those 3 capacitors or more in series. C1, C2, and C3 are in series. Series, they lie along the same pathway. And the pathways we'll generally call branches. So this is all just one branch here, because it's one singular pathway. But we can also have what is known as parallel configuration. And for parallel configuration, what we have is that they lie along different branches. So we could have a capacitor like this, a capacitor like this, another capacitor like this, and we can kind of keep on going and have more up here, more down here, dot, 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 and ultimately have these all kind of connect back and go like this. So I'm just showing 3, but we could have n capacitors, and C1, C2, C3. We have C1, C2, and C3 are in parallel. We can go ahead and say that these are connected back to a source potential. And there we go. So what? Well, we've got different things going on. For here we have the main branch. And then what happens? We've got right here. This is called a junction. The main branch reaches a junction and then splits off into some tertiary or secondary branches. So we could call this like a branch 1, a branch 2, and a branch 3. We can call this the main branch. We can name them however we really want, but the main thing is that when we have capacitors in parallel, they are not on the same branch. They are on separate branches that are separated by a junction, which is different than something like this, right? These 3 are on the same branch, one singular branch. These three are on their own separate branches. We can have a combination of series and parallel. We'll get into that. But right now we just want to note the differences between series, and just parallel. Three different branches. 1, 2, 3. Junction, main branch. This is all one branch. You just say the main branch, sure. It's just one, so it doesn't really matter. But there we go. We got these two different ways that we can configure capacitors in general, and what we want to note is how they work in these two different configurations. They do not work the same way. So we're going to start with two capacitors in a parallel configuration and sort of unravel it and see what we can extract out of it. Parallel happens to be the easiest one to look at, in my opinion. So let us do that. Let's consider two capacitors, C1 and C2, that are in parallel and connected to some source potential. All right. Finish erasing that. We'll do just that. Two capacitors in parallel. So, how do I want to draw that? I just go like this. Make it very apparent that they're on separate branches. This comes up, this goes over, and then we'll connect them to a source potential. And we've got this. So we've got some C1 there, we've got some C2 there, and we've got our source potential there. So C1, C2, those are two different capacitors. Maybe they have the same capacitance, probably not though, not necessarily. And our source potential. So what we want to understand is how this all comes to play with respect to them being charged up. So we hook them up, enough time goes by, the capacitors are fully charged. What do we have then? Well, let's think about this. Let us trace back these terminals to how they're connected to the capacitors themselves. So I'm going to go ahead and take this and say, well, this traces directly back to both this plate and this plate. So the plus terminal of the source traces directly to the plates of both capacitors on this side. All right, so let's go ahead and look at the minus terminal and come over here. Well, the minus terminal this side traces directly over to that. And on this side, traces directly over to that. So, again, we have the same sort of thing here. Minus terminal of the source. Traces directly to the other place. So what does this mean? Well, it means that this plate is a direct extension of this terminal, and this plate is a direct extension of this terminal. And this plate and this plate are both direct extensions of this terminal. So what happens? Well, if this acts like this terminal and this acts like this terminal, the potential difference across this particular capacitor has to be the same as the source. Likewise, if this acts as an extension of the positive terminal and this plate acts as an extension of the negative terminal, the potential difference across this capacitor has to be that of the source. which means that the potential difference across each of these capacitors has to be the same. And that is always going to be the case when we have capacitors in parallel. Since the terminals of the source trace to be directly connected to the plates of both capacitors, we must have that delta V1 is equal to the source potential and delta V2 is equal to the source potential, where delta V1 and delta V2 are the potential differences across C1 and C2 respectively. So ultimately what we're saying here is, we've got some delta V1, the potential difference across C1, and we've got some delta V2, the potential difference across C2. And those have to be equivalent to the potential difference of the source because of how the plates trace directly back to the terminals of the source. Whew. All right, so here's a question for you. Will the charges separated, Q1 and Q2, be the same? Well, if we go back to the individual capacitors, we have that C1, by definition, will be Q1 divided by delta V1. And C2, by definition, will be Q2 divided by delta V2. The charge it stores, or the charge separated between the plates, divided by the potential difference across the plates. Well, but in this particular case, this goes to Q1 divided by the source potential, and this goes to Q2 divided by the source potential. So are Q1 and Q2 the same? Only if C1 and C2 have the same capacitances. If C1 and C2 are two different capacitors having two different capacitances, then we must have that Q1 and Q2 are two different amounts of charge separated. This charge separated produces, or is correlated directly with, the potential difference across the plates that define the capacitance of said capacitor. All right, so what we want to do with this is say, is there any way that we could simplify this? Is there any way that we could replace those two capacitors with one singular capacitor that ultimately does the same thing? You may say, what do you mean does the same thing? If it's only one, it's not doing the same thing. I say, well, by the same thing, I mean stores the same overall energy. After all, that's what capacitors are known to do. They store energy. So can we replace these two singular capacitors, C1 and C2, with one singular capacitor that stores the same energy, does the same job? And if so, what is the capacitance of that singular capacitor? So let us find what is known as CEQ, the equivalent capacitance of the system. CEQ has a particular capacitance such that when connected to the source potential, it will will store the same amount of energy as C1 and C2 together. All right, so how are we going to do that? Well, that's a good question. Let us start with this. What happens if we just go ahead and say, let me put this up here, reference this. We just go ahead and say, hey, we're going to take another system that only has one capacitor that's hooked up to the same source potential, and we're going to try to equate them. So we're going to go like this. Source potential, singular capacitor, like this. Source potential, bad scripty there. Source potential, and then the capacitance of this capacitor is CEQ. All right. So we say that we want it to store the same energy. We want it to do the same thing that this network does. Well, let's start off with defining the capacitance of this capacitor. CEQ is going to be equal to, well, the total charge stored divided by the source potential. When we have one single capacitor, that is how we define its capacitance, right? So that is its definition. When it's fully charged, and that's what we're assuming, fully charged. So the question becomes, how do we get this out of those two? And what we can see here is that the definition of these singular capacitors relies on the charges that are separated, Q1 and Q2, and the source potential. This one relies on the total charge separated and the source potential. What's the total charge that's separated in this system? Well, we've got some Q1 here that's separated and some Q2 here that's separated. Should it stand to reason that the total charge that's separated here is Q1 plus Q2? That seems reasonable, right? Well, let's look at this. We want to take these two capacitors and somehow make CEQ. Q over E1, excuse me, Q1 over E, Q2 over E, Q total over E. Well, they have a common denominator of the source potential. And we've already come to the conclusion that it makes sense that Q1 plus Q2 would equal Q total. So let's check this out. Q1 over over E plus Q2 over E is equal to the quantity of Q1 plus Q2 over E, which, hey, if Q1 plus Q2 is Q total, we're just going to go ahead and say Q total over E, which is equal to CEQ. Well, this here, this is the definition of C1. This is the definition of C2, and if indeed these two add together to give us Q total, we've got that C1 plus C2 is CEQ. That all seems very reasonable, does it not? It does, but we have not used any energy considerations at this point in time. So what we want to do is sort of look at it in terms of energy then and make sure that that is the case. So we just go ahead and do that. How are we going to do it? Well, we know how energy works, right? We already derived out or have an expression for the energy stored by a charged capacitor. So let us check this out. Making sure the energies stored are the same between the two systems. So for this system, two capacitors. In parallel. U total energy stored is going to be the energy that capacitor number 1 stores plus the energy that capacitor number 2 stores, which will be, in general, 1/2 multiplied by the capacitance multiplied by the potential difference across that capacitor squared plus 1/2 times the other capacitance multiplied by the potential difference across that capacitor squared. So this is still really general here, but we also have that they're in parallel, so this potential difference and this potential difference have to be equal, number 1, and since those are the only 2 capacitors in the system, they also have to be equal to that of the source. So this U total is also equal to 1/2 C1 times the source potential squared plus 1/2 C2 times the source potential squared. Well, what is this going to be equal? This is going to be equal to 1/2 common factor, and then we've got this other common factor of E squared. We'll pull that out on the other side, and we're left with the C1 plus C2 times E squared. All right, there's the total energy stored by this network. Now let's look at the equivalent capacitor. U total energy stored, is going to be equal to 1/2 multiplied by the capacitance of the capacitor, which is CEQ, multiplied by the source potential squared, because that's the potential difference across these plates. So what do we have here? Are these 2 things equal? And what do we have? Equal if CEQ is equal to C1 plus C2. Check. That's what we've just said right there. And that must be the case if we have the same amount of energy stored between the 2 systems. So really, we've done it in 2 different ways. We've done it straight up by just kind of analyzing the systems and saying what should be the case, and then directly looking at the energy stored and reaffirming that, yeah, the equivalent capacitance of the system is the straight across sum of the individual capacitors. So, 4 capacitors in parallel. The equivalent capacitance V is given by C EQ is equal to the sum from I equals 1 to N of C sub I. This is just summation notation. What does this mean? We're summing over however many capacitors we have in parallel. N of them, maybe there's 2, maybe there's 3. Right now we only have N is equal to 2, but in general we could add up 1,000,000 capacitors that are all connected in parallel with one another and find out what the equivalent capacitance is, and it's just the straight across sum. C1 plus C2 plus ... plus C sub N. There we go. That's what we've got. And we also have that the potential differences across the individual capacitors has to be the same if they're in parallel. Now we don't want to say that it's always going to be that of the source potential. That depends on some other things going on. Here we only have that one parallel section. If we start having other sections, then the potential difference could get split up. And since both plates on both sides are directly connected to the terminals of the source, that happens to be the case here. But in general, we also have that delta V1 is equal to delta V2 is equal to delta V sub N. They all have the same potential difference across their plates if they are in a parallel. So that is something else. So there we go. You may say, well, why do you want to have 2 if you could just replace it with 1? There could be different reasons. Maybe we have limited capacitances for our individuals and we want to make a certain capacitance. Like, hey, I don't have a 200 microfarad capacitor. I just got two 1/100s. How do I make a 200 microfarad capacitor system? Hey, I put the two 100s in parallel. Now I've got a 200 microfarad capacitor system, for instance. Or maybe we need two separate capacitors in the system, but we want the overall energy stored to be a certain amount. There we go. All right, so that is a parallel. What about series? Well, but series is going to be the same? And I'd say, are you serious? Of course not. Why bother making a distinction between the two if they just turn out to be the same? So, let us now look at the series case. And again, we'll just consider two capacitors. If we can do it for two, we can do it for n in series. Two capacitors in series. So, draw this out. I'm going to have the C1, the C2. We'll go ahead and connect it up with some source potential. C1, C2, great. We've got ourselves the positive terminal of the source potential, the negative terminal of the source potential, and then what do? We do the same thing that we did before. We'll look at how these terminals trace back to the plates of the capacitor. So this terminal here traces back to this plate, the left-hand plate of C1. Plus terminal traces back to the left plate of capacitor number 1. All right, what about this side? Well, this side, we've got the negative terminal traces back to be connected to the right plate of C2. Minus terminal of the source is connected to right plate. C2. Well, this plate then acts as an extension of this terminal. This plate then acts as an extension of this terminal. What does that mean? Well, that means this, that the potential difference between this plate and this plate have to be that of the source. So this total potential difference, delta V subtotal, total potential difference across the whole section there, delta V total, must be equal to that of the source. Again, because of the logic that these two are extensions of the terminals there. But these two capacitors have to have their own source potentials themselves. We have to have that there's some delta V1 and some delta V2. So do we just add those together? Delta V1 plus delta V2 is equal to delta V total? Maybe. Maybe not. What we got to understand is what's going on in this interior spot right here. So we have the capacitors in between their plates. It's either vacuum, air, or some other non-conductive material. If there was a conductive material in between the two plates, you could never get charge separated on them because it would always have a way of neutralizing. You don't want that. That's not how capacitors function, not what we want them to do. So in between the plates of a given capacitor is basically unconnected material. This plate is not electronically connected to this plate. So what does that mean? Well, this plate's not connected over here, this plate's not connected over here, so this whole interior region right here, this interior inside region, is not connected to anything. Not connected to the battery, it's just connected to themselves. This plate's connected to this plate, that's it. So what? What happens? Does anything happen? Well, let's look at this in a little piece by piece here. Since this one's connected to the positive plate, and this one's connected to the negative plate, electrons are going to be taken off of this plate and swept around and deposited on this plate until the potential difference is such that, until the charge separation is such that the potential difference between this plate and this plate is equal to that of the source. So we're going to assume that enough time's gone by, that's the case. So we've got positively charged plate, negatively charged plate in equal amounts. Okay, great. Does anything happen to that interior region? And the answer is yes, something happens, but how if it's not connected to anything? I say, well, it's still conductive material in between here. What happens when we take a charge and bring it near a conductive material? Well, you get some polarization effect, right? Some redistribution of the electrons that can reassemble themselves. So we've got this, right? This is a positively charged plate. Positive charge attracts negative charge. And in this interior plate, this is completely electronically neutral. Same number of protons and electrons. But electrons can swim around. Some of them, conduction electrons. So what's going to happen? They're attracted to this excess of positive charge. So some electrons from this plate sweep over here onto this plate. Until, well, there's equal amounts between this positive charge and now the negative polarization charge. Since those electrons came from over here, what happens? Now there's a deficit of electrons here. There is exposed protons or an abundance of protons. That matches out how many electrons are over here. So what happens? We get, again, this polarization shift that produces a mirroring of the charges on the outside plates. Polarization shift. So now we have just as much negative charge as we had positive charge here. This should be positive. And just as much positive charge here as we have negative here. So it's the outside plates that are really controlling what's going on here, and the outside plates have the same amount of charge, just opposite. Those electrons came from this plate. So we must have that the charge separation on this plate is equal to the charge separation on this plate, considering these two things. But really, it's the outside that's the charge separation. This is just a polarization shift. This right here, this is still electronically neutral overall. This and this is not. We've got electrons are all the way over here from this plate. So in this particular case, what we have is that there is some Q1 and there is some Q2. Those are the charges separated, where Q1 must be equal to Q2. Charge separation is the same on each capacitor. All right, so what can we do with this? Well, we can go ahead and start looking at the definitions of these individual capacitors. We have to have that C1 is defined as Q1 divided by delta V1, and that C2 is defined as Q2 over delta V2. All right, so we've got those two things going on, and we also note that delta V1 plus delta V2 has to be delta V total. There's no way around that. Delta V1 plus delta V2 must be delta V total, which is equal to that of the source. Between those two plates there, total potential difference of constant. So ultimately what we find in series is that the potential difference gets split up amongst the individual capacitors, such that the total gives us back that of the source. And that the charge accumulations or charge separations have to mirror each other, because it's really, again, the outside plates that have the true charge separation. So we've got Q1 is equal to Q2. And because this, again, this interior is just a polarization shift, isn't really taking charges off the plates due to this source potential and putting it over on this plate, truly separating it out. We've got that this Q1 is equal to Q2 is actually the total charge separation itself. We don't add them together, Q1 plus Q2, because the inside, again, is a mirroring effect. It's It's not the true charge separation. The outer plates is the true charge separation. So that's what we end up getting with this. So when we go ahead and look at these two expressions here, we have that this is equal to Q total divided by delta V1, and this is equal to Q total divided by delta V2. What happens when we start comparing this to the equivalent system? We've already drawn it out. We'll just draw it out again. It doesn't change. We just have one single capacitor, CEQ with the source potential, and CEQ is defined as Q total divided by the source potential. So what we want to do, again, is be able to take Q1 and Q2 and put them together some way that we get CEQ out of it, get the equivalent capacitance. So how are we going to do this? Well, the easiest thing to look at is what they all have in common. They all have Q total in common. Let's look at inverses, because then they all have a common denominator, right? So what if we go ahead and say 1 over C1, well, that is going to be equal to delta V1 over Q total. 1 over C2 is equal to delta V2 over Q total, and 1 over CEQ is going to be equal to the source potential divided by Q total. Shortcutting it, just Q sub T. So how do we take these two capacitors and make this one? Well, Q1 plus Q2 is equal to the source potential, right? So what happens if we just add these together? Let's look at this. 1 over C1 plus 1 over C2 is equal to delta V1 over Q total plus delta V2 over a Q total, which is equal to delta V1 plus delta V2 over Q total, delta V1 plus delta V2 over Q total. And what does that give us? I'm running short on room. Let's just drop it down right here. That's going to go ahead and give us whoosh, delta V1 plus delta V2. Hey, that is the source potential divided by Q total, which is equal to 1 over CEQ. So what do we have? 1 over C1 plus 1 over C2 is 1 over CEQ. So let us write that out, generalize it to N capacitors, and ultimately solve this for CEQ. So if we want to solve this for CEQ, CEQ is equal to the quantity of the sum from I equals 1 to N of 1 over C sub I to the negative 1. Inverse of the sum of the inverses. And again, not again, but this is because if we take 1 over CEQ is equal to 1 over C1 plus 1 over C2, and we want to solve this for CEQ, we have to take the inverse of both sides, right? So we'd have that CEQ is equal to the quantity of 1 over C1 plus the quantity of 1 over C2 to the negative 1. Inverse of the sum of the inverses. So this is a more condensed way of writing this out, but ultimately this is the quantity of 1 over C1 plus 1 over C2 plus dot 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 plus 1 over C sub N to the negative 1. Add completely different, right? Completely different. Inverse of the sum of the inverses for capacitors in series, where it's just they add straight across when they are in parallel. So the last thing that we have with this is also Q1 is equal to Q2 is equal to Q sub N. When they are in series, they have the same charge separations across the individual capacitors. When they're in parallel, they have the same potential differences. And it's pretty much that. Whoa, whoa. Alrighty? All right. So there we go. More to come. More to come. Until then, be well.